Hello and welcome to this manufacturing process technology part 2 module 25. We were talking in the last module mostly about how to design the tool surface given a certain workpiece geometry or a functional relationship on the workpiece surface, and we arrived at in general 2-dimensional and 3-dimensional shapes of the tool given a certain workpiece profile that has to be finally achieved through the die sinking ECM process. Today we are going to look into a little different aspect. Once we have estimated the shape of the tool, the other aspect which is important is how to control the electrolyte flow, and the whole idea here is that there should not be any flow separation, or there should not be any local eddies or local circulations or recirculation zones which are formulated in the path of the flow, so that there may be issues related to the non-uniformity of conductivity and thereby the material removal rate. So some of the points we should generally remember are that generally in the example that you had noted in the last module where we tried to estimate a shape, the method used to solve the y values, if you may remember, there was a functional relationship between the yt and the xt's. Okay, so this is generally applicable to smooth surfaces with gentle variations, whereas the applicability can only span in domain where the current flow lines which are formulated are by and large parallel to each other. But however, when the electric field and therefore the current paths they get staggered, or they get concentrated, maybe because of some small points where the field is centered, particularly at the corners or at the tips, then it is very difficult to maintain the parallelity of the various field lines or the current flow lines, and therefore the closed form solution that we sort of obtained by just a function mapping does not work in that case. So for more complex shapes and for surfaces involving sharp curves and sudden changes, a sort of a solution of what would be the electric field density with respect to the space coordinates would be a very important aspect for estimating the actual MRR at different places on the same surface. Okay. So the closed form expression of the workpiece surface is not available, and typically in this or in CAD wherever necessary, there is a strategy that we follow, that we divide the whole surface into synthetic curves and try to join the synthetic curves together, small segments probably together, and each of them would have a functional relationship, and that way we could estimate the overall topology of what is to be done or machined. So the surface can be divided into small straight or curved segments of known geometry, and then a method can be just used where mapping of individual segments onto the tool side to develop the whole tool map or the tool surface map is created, so that the final tool shape can be estimated. So now if once we have looked into the shape estimation, the other point, as I just mentioned a minute ago, is how to design for the electrolyte flow. The electrolyte flow is a very important component, because we want to avoid any kind of recirculation zones or any kind of eddies where suddenly there can be a shoot of the conductivity. Also we want to avoid any kind of flow separation suddenly, where because of the electrolyte not being available, there is less machining and eventually creation of a boss or a ridge because of improper reach of the electrolyte. So a sufficient electrolyte flow between the tool and the work piece is necessary to carry away the heat and the products of the machining, and to assist the machining process at the required feed rate, producing satisfactory surface finish. So also one should avoid such kind of flows where there may be possibility of cavitation, or because of sudden separation of the flow there may be a tendency of bubbles to get generated in the flow, or sudden, let's say, turning in the flow direction, there may be some kind of a pressure loss, and because of which there may be a mixed phase which may come. There can be stagnation, there can be vortex formation, and so all these should be avoided, since this lead to a bad surface finish, and that is what we normally do not want to do in ECM. So one basic rule is that there should be no sharp corners in the flow path. As such, the flow should be smooth and laminar. All corners in the flow path should have a radius of at least about 0.7 to 0.8 microns millimeters, about 700 to 800 microns. And the initial shape of the component generally does not comply with the tool shape, and only a small fraction of the area is close to the tool surface at the very beginning. Slowly, because of the die sinking nature of the ECM, a parallelity is generated in the workpiece surface, and the fields that come in are more or less uniform. So the problem of supplying the electrolyte, particularly at the initial stages when there is no parallelity between the tool surface and the workpiece surface, is generally solved by using some flow restriction techniques. This is a very ideal case where you can see that the tool surface is almost parallel to the workpiece surface. This seldom happens because ECM is normally used as a die sinking process. So how do we do flow restrictors so that the flow can be routed well and it can reach all the zones or areas where machining needs to be carried out? So we will actually look at that just a little bit later. First of all, let us now see what could be different situations because of the inappropriate flows or inappropriate presence of the electrolyte in various regions on the workpiece surface. So in many situations when the initial work surface conforms to the tool shape, as you can see here, the work surface is quite conformal. The machining process itself causes the formation of a boss or a ridge in the workpiece. So you can think of it that just because from case 1 in the previous figure where we showed that there is the electrolyte being flown in a direction perpendicular to the tool axial center and away from the tool axial center into the outward direction, there is a separation of the two flow streams because these gaps here between the workpiece and the tool on both sides are very small. So the separation is somewhere around this central plane, where there is always a possibility that because of such a sudden separation and a laminarity of flow which normally happens in such a small gap as the interelectrode gap, there is less electrolyte which comes in this region, or there is starvation in this particular region, which is shown by this sort of a dark circle. So because of the presence of less electrolyte in this region, obviously the machining rates here would be very small. So the MRR is small, okay, and because the MRR is small, you may find out that eventually there is a ridge which is getting developed or a boss which is getting developed, as you can see here. Boss is a projected structure of from an otherwise flat surface, as you can see, or maybe some kind of a ridging effect like this, and this is because generally the flow separation causes a sudden flow separation causes a zone and a region where there is a sudden starvation of the electrolyte which would happen. So a tool with an electrolyte supply slot is very simple to manufacture, but again the design has a constraint that such a slot may leave small ridges on the workpiece, which is not desirable. We don't really want a separate sort of a ridging or a bossing of the workpiece because of the electrolyte flow or the electrochemical machining process. The whole idea is to make the machining happen as flat as possible. So if we wanted to avoid this problem, the best way to do that would be to make this electrolyte slot which is dispensing the electrolyte very narrow, so that there is a small stream of fluid which can come, and then this may result in a very low a small region of separation zone, and so the effective ridge dimension or the boss dimension which may be formulated is so small that it is more or less insignificant in comparison to the plane surface of the tool. However, the ridges can be made very small, therefore by making the slots sufficiently narrow. Obviously one needs to ascertain that the width is enough so that there is proper supply. It should not be that the slot is so small that the supply is constrained, and then because of that constraint there is another ridging or a bossing effect which may happen, and it should have just enough to supply the electrolyte, but it should have not a very high width, so that overall the ridging effect can be minimized. The flow from a slot would otherwise take place in a direction perpendicular to the slot, and the flow at the end is poor. So the slot should be terminated generally at the corners of the workpiece surface, otherwise that may result in another issue related to the formation of a secondary boss at one of these surfaces. So there are several designs that have been illustrated here. You can see this design A as well as design B, and what one can find out is that there are many aspects of both the designs here. One is that the tool also getting eroded during the ECM process. One must remember that there is always a minimum dimension that is needed between a slot and the end of the tool, so that there is no leakage or there is no machining of the slot all the way to the edge, where there may be a leakage of the electrolyte from the side of the tool. So that should not happen. So the distance typically between the tip of the slot and the corners should be at least 1.5 mm. That is what the thumb rule of design says while designing these tools, whereas a slot with a width of 700 to 800 microns is normally recommended. So the slot should not be more than at the most about 1 mm. It is a better idea to have it in the sub millimeter range or sub millimeter domain. So when the workpiece corner is rounded, like for example in this particular case you can see the corner being rounded, the slot end should be made larger, because obviously the question here is that the electrolyte should flow out radially in all the directions so that it reaches all tool corners and covers the whole surface. Had it been that in this particular case we would have a smaller slot and an ending as is visible in this particular figure, there may be a restriction of the flow, because the flow may not be able to get enabled in this particular case over the whole surface. So it is, I think, a better idea. So when the workpiece corner is rounded, the slot end should be made larger, okay, as you can see here in this particular case. The shape and location of the slot should be such that every portion of the surface is supplied with electrolyte flow, no passive area exists. Let us look at two example problems here, case A and case B. In the case A, for example, you can see the presence of a passive area where the electrolyte does not reach, because obviously the electrolyte would ooze out in perpendicular directions as shown by these arrows, and the electrolyte that oozes out in this particular region actually goes outside and it cannot be guided back into the passive area. You have to remember that there is a gap between a tool and the workpiece. So this is a open area, there is no gap, okay. So the electrolyte is lost here, and so therefore this region which is shown by this dotted structure is the region where the electrolyte is not received. There is another case here where electrolyte starvation happens because of sudden bending. You can see there that this slot is, you know, it's a corner slot, or it's a suddenly bending slot where there is a sharp corner, okay, and so the flow direction changes all of a sudden, because of which there is a formulation again of this dotted region which is the passive area. So these designs are inappropriate, and somehow it needs to be designed in a manner so that these passive areas shown by the dotted image here are eliminated. So how do we do the design? So here the same slots are curved rather than straight slots, and as you can now see probably that, you know, as the perpendicular as the electrolyte is always oozing out in a perpendicular manner, and you know, there is always the closure of the passive area, because now the electrolyte is oozing in all different directions, in which is perpendicular to various portions of the curve which describes the slotted region. Similarly, because of a smooth chamfering and a curving of an otherwise available corner between the slots, the full coverage of the electrolyte is seen in this particular area. So the correct design of the slot is shown in these figures, and obviously in some cases it may be mandatory to use a reverse flow tool where the electrolyte may flow from outside to inside, and sometimes a reverse flow tool is used to cut accurately and produces a superior surface, but the process is more complex and expensive and is not generally recommended. So if I were to take the electrolyte from outside and send it into the tooling region, the guidance of the electrolyte may not be a very simple issue to be done. So the techniques for controlling the electrolyte flow when the initial work surface does not conform to the tool surface are illustrated here. If this is case 1, for example, where you can see that it's an inclined surface on which ECM machining is being done, and similarly in the case 2 right here you could see again the surface is not very smooth. There is a sort of a boss coming out of the whole surface. It is not a flat surface. So in either of the cases, as the tool does not conform to the surface, there are going to be obviously different field values between the tool and the workpiece electrode. So the general rule in order to guide the flow in a proper manner is to put a flow restrictor. In this particular case you can have a dam like structure as shown here, which acts as a guiding mechanism for the electrolyte to ooze out between the tool electrode gap here in this region, okay, and the flow restrictor must be adjacent to the area of the initial close proximity between the tool and the workpiece, so that you could create a substantial confinement of the electrolyte before the electrolyte leaves the inter-electrode region. So it should also not increase the flow path substantially when we do flow restrictors, and it must be either at the entry or at the exit position of the electrolyte. These are two different cases. Case 1 is at the exit position of the electrolyte, case 2 is at the entry position, and you can see here that just because of the presence of this restrictor, which again I would like to reaffirm is not a part of the surface. You are basically putting this restrictor by just either sticking it to the surface or welding it to the surface or placing it and bonding this somehow in a semi-permanent capacity to the surface. Similarly are these end restrictors here. So it can be removed as the machining has been carried out or it is completed. So that is how you can confine the electrolyte in certain spaces where otherwise it may be difficult to hold the electrolyte for longer amount of time. The areas on a tool where the electrochemical machining is not desirable need to be insulated. So that is why the sides of the tools are almost always insulated, and so are the axial centers of the tool from which the electrolyte comes out or oozes out. So it ensures that there is no machining in the sidewise area, and then it can remove the possibility of taper. So in die sinking also the tool should be properly insulated to minimize the stray machining effects which may otherwise happen. In this particular case, for example, when you are having this complex shape of the tool being imprinted into the workpiece, there is a possibility that the sides may get shallow and it may not be able to attain the correct topology. But if there were insulators, as you can see in this particular case, these two regions are the insulator regions of the tool, then the tool may be able to die sink more appropriately in comparison to the one without insulation. So the figure on the right shows the ECM process with and without a proper insulation. Again here this is without the insulation. You can see the regions developing shallow and the die sinking not appropriately done, and with insulation the same problems do not arise. Further, the insulation must be tough and securely bonded to the tool surface, because obviously if it comes out during the machining operation, it is going to jeopardize the surface of the tool over which it was pasted, and the tool may change shape and size because of the coming out of the insulation. It can also be provided by securing the reinforced solid plastic material to the tool with epoxy resin cement and plastic screws. The insulation can be done by applying a synthetic rubber coating on the artificially oxidized copper tool surface, and the boundaries of the insulation layer should not be exposed to high velocity electrolyte flow, which may tear up the glued layer otherwise. So that is how you design for the flow path. You also design for the insulation on the tool. The other issue is choosing the right electrolytes, because obviously electrolyte is the main active element of this whole electrochemical machining system. It basically performs 3 different functions. One is completing the electrical circuit, allowing the large currents to pass by. Now there is sustaining the required electrochemical reaction to happen for a longer time, so that the material removal rate can be continuous phenomena. Material removal can be a continuous phenomena, and then obviously carrying away the heat generated from the waste product. So for the first function to accomplish, that is completing the electrical circuit, the electrolyte ideally needs to have a large conductivity. Obviously the conductivity of electrolyte are nowhere near the metallic conductivities, probably orders of magnitude lower in comparison to the metal conductivities, but still they are highly conducting, and if the conductivity is more, ideally the material removal rate is more, as we have seen earlier in all our derivations. The second function of sustainability of the reactions basically depends on the fact that the electrolyte should continuously dissolve the work material at the anode, and a discharge of metal ions on the cathode should not occur. So there has to be a combination of the processes of dissolution as well as a process of precipitation simultaneously, so that on one hand the workpiece gets dissolved and the redeposition on the tool does not happen. So generally the cationic constituents of the electrolytes are hydrogen, ammonia or alkali metals. So by and large the dissolution of the anode should be sustained at a high level of efficiency. Hydrogen of course is also an agent which can in dissolved state reduce the conductivity of the electrolyte. So we should avoid the presence of gaseous hydrogen dissolved in the electrolyte. However, if hydrogen is available as hydrogen ion for dissolution of the basic salt which makes the electrolyte, that is more appropriate for having a good conductivity of the electrolyte. So the electrolyte must also have good chemical stability. It should not vaporize, it should not create toxic fumes, etc. So generally it should have overall safety, as non-corrosive as possible. ECM tools otherwise are insulated at all different regions because of avoiding the problem of corrosion and dissolution. The electrolyte is in continuous contact with the different metallic parts of the different systems associated with the tooling, and obviously it should be inexpensive from the point of view of the process economics to happen. These are some of the type of electrolytes which are normally used. You can have for iron based alloys and dissolution of iron based alloys, chlorine solution in water. This is a very common example, the brine solution, normal sodium chloride 20% by weight in water. For the nickel based alloys you could have a combination of hydrochloric acid HCl or a mixture of salt water and H2SO4 sulfuric acid. Again for titanium based alloys you could have a 10% hydrofluoric acid with again 10% HCl and 10% HNO3. For these cobalt chromium tungsten based alloys you could have a normal NaCl normal kitchen salt based solution, or for tungsten carbide you could have a very strong alkaline solution serving as the electrolyte. So these are some of the different kind of electrolytes as regards the different single phase or alloyed systems. I would also like to give a brief schematic of the machining plant and how it typically would look like. So you should have a system of circulation here where the electrolyte and the precipitate are sort of pumped from a tank into the main zone of machining. The broken lines coming here are basically splashes of the electrolyte. This is the zone of machining here between the tool work piece. The electrolyte is pushed into this coaxial central region of the tool through which it emanates out at certain pressure. You have a low voltage high current transformer rectifier for supplying the voltage signal between the tool and workpiece. You also have a control panel to drive the amount of power that you get to the system for executing the machining process. There is a tool drive which senses the gap and tries to reduce the gap as the machining process happens between the tool and electrode. As you have seen earlier, there is also always a possibility of getting a constant equilibrium gap between the tool and electrode as a function of time. Overall, the machine body is highly insulated in nature. There are many regions which have to be protected from the erosion or the corrosion of the supplied electrolyte. There is of course an air blower to discharge hydrogen, a tool holder, and insulation on the tools. You can see these two insulation ends or insulated ends of the tool. There is a working surface, there is a fixture, an insulator and a base. Sometimes it is a good idea to filter the electrolyte because it may have some dissolved particles, some matter which may create problems related to the surface finish or other machining parameters. So a strainer or a filter is needed, highly needed for purifying the electrolyte before supplying to the zone of machining. And obviously the material that is removed is carried back by the electrolyte by circulating the electrolyte from the machining zone or chamber into this sludge discharge tank which collects the dissolved electrolyte with metal particles. So some of the design guidelines for such electrochemical machines: the stiffness in the material of the components need to be thoroughly evaluated. There should not be any wobble of the tool holder, so that whatever is to be machined has a certain degree of precision. We know that there are large amount of viscous forces between the flowing electrolyte, particularly because the gap is very narrow, and the electrodes. So the machine must possess enough rigidity to sustain minimal or negligible deflection of the tool with respect to the workpiece, and also sustain any kind of vibrations which may be put in because of the tool drive unit or the motor because of its imbalance. So a change of temperature may also cause relative displacement between the tool and the workpiece. Design should take care of this aspect. Wherever possible, one should use non-metallic materials which are not prone to corrosion, which can avoid corrosion. The workpiece holder is highly prone to anodic attack, and therefore it needs to be surface passivated. Titanium is a good material to passivate the surface. It's a stable metal. As most of the components are in close proximity to the electrolyte, they are exposed to corrosion, and so therefore it is a good idea to choose the material in such a manner so that they sort of, wherever there are non-working zones in the machine, should have a shielding overall from the electrolyte, and they should possess identical. So their material normally should be chosen in a way that they do not possess any identical electrochemical behavior. Typically insulators are the most preferred materials in this particular purpose. So this brings us to an end of the electrochemical machining in general. There are many other variants of the electrochemical machining process, like electrochemical grinding, electrostream drilling, which we will probably cover in the following module. But in the interest of time, I would like to close this particular module, and in the next section we would talk about some associated processes related to whatever we have learned in the mechanical removal as well as the electrochemical removal of material. Till then, thank you and goodbye.